but that would have been 0. And then it would have been minus the bottom, which is x squared minus 4, because you have to subtract it by the axis of rotation.
Okay, so.
Oh, that's why I did wrong, because the axis of rotation is on the top.
Mm-hmm.
The negative would make the x squared a positive, which is why my answer. Okay, that's what I did wrong.
Okay. Are there any others that we want to go over on the volumes of revolution one, volumes of rotation? Yeah.
The free response is the part B, because I didn't have to write it on the top, but I was wondering why the
Wait, this one or no, this one? Yes.
1 minus e to the negative 3x would be first rather than second.
Okay. So when we figure out, okay, first let's just start at the beginning. If we were doing this problem, how do we know that this is a washer method and not a disk method? So that's part of it. It doesn't touch it, so we can see the shaded region is not up against the axis of rotation. So anytime you see space, so right here, I can see that there is space between the shaded region and the axis of rotation. Anytime there's space there, it's going to be a washer method problem. So when it spins, it's going to make, I wish they called these donut problems, because I don't think in terms of, like, I don't like build things, so I don't picture washers all the time, but if you said donuts, I'd be like, yeah, donuts got a hole in the middle, that makes sense. Like, as opposed to like a little washer, like, I mean, I guess now I picture washers because I've made like I've like put a lot of furniture together for my house, but I feel like if I was a teenager, I would not be picturing washers. Anyway, that's beside the point. So that's why it's a washer method. And so if we remember the washer method, we have pi r squared minus pi r squared. And so the big R is created by, we're going to do in terms of x, so we're going to do top minus bottom. And the big R is going to be created using the axis of rotation in a curve, and it's going to be the curve that's furthest away. So we're going to do top minus bottom. The top is always going to be the axis of rotation. So it's going to be top minus bottom. And then the little r is going to be top minus bottom. Because the big R is always, the big R is for the radius that is the furthest from the axis of rotation. And so this curve right here is the furthest from the axis. So top minus bottom, top minus bottom. So the little r is going to be created, and I shouldn't really call it little r because it's not little. It's going to give us little r. I'll do big B for big bottom and little b for little bottom. So little b is root x, and then the big bottom is going to be e to the negative 3x. And then the top in both cases is that axis of rotation. Is everybody comfortable with that point of intersection, how they got that? Yeah, we could all do that on our own. Does that make sense? So they graphed those two curves, and they just did second trace number 5. just to see where that intersection point was. Now, we are going to go ahead and do this, actually. That's an important step of this because we need this on our calculator, actually. So we can't avoid doing what they did. We actually have to do it because we need those decimals on our calculator. And you're going to have to do stuff like this on the AP exam. You can't just use those. You can't be like, oh, the AP exam likes me to use 3 decimals. So I'm just going to take this and use the first 3 decimals, because if you round in the middle of an AP problem, then your 3 decimals at the end of the problem are going to be wrong. Does that make sense? So the AP exam people are saying, hey, at this point you are a college level student, you should be comfortable enough with your calculator that you can store answers and things like that, so that you are only rounding at the end of the problem. And the rest of the time you have decimals stored into your calculator. So what we're going to do is we're going to go ahead and type these functions in. E to the negative 3x, square root x. This is kind of giving us a clue that our window is going to be very, very small, 0 to 1. So I'm just going to do like negative 2 to 2, knowing that this window is going to be a little bit bigger than what they have there. So my window is quite a bit bigger, but I can see that intersection. And so now I'm going to do second trace number 5. Just getting over there, getting that intersection. And my whole goal for what I'm doing right now is I want that exact decimal in my calculator so that I can use it to do the computations that I'm about to do. Okay, so enter, enter, enter. Okay, so I have the decimal in my calculator right now. That was my goal. So right now I'm going to hit second quit. And if I hit the X button, this X button right here, if I hit the X button right now and press enter, that decimal is on my screen. Everyone got the decimal? So now I want to store it as something else. So I'm going to hit store. Remember, that's right above the on button, STO. I'm going to store it. And then I usually store as A. So I'm going to store it. I'm going to store it as anything but X because I typically use X as a variable. So I'm just going to store it as something else. Okay? All right, so from now on, you have 2 options. You can say, let this decimal equal A, and then you can use the letter A on your paper, or you can keep writing the decimal out and just know that you stored it as A. It is up to you. Okay, so what I chose to do is I chose to write out the decimal, but I knew that I was using the letter A. Does that make sense? Okay, so now I'm writing my capital R as top minus bottom, and I'm writing the lowercase r as top minus bottom. Does that make sense? Top minus bottom, okay? And I've got pi capital R squared minus pi lowercase r squared. And then what I did is I pulled out the pi to make it easier for me to type this. Everyone comfortable with that? Okay. Yes, people typically pull out the pi. Yes. Mm-hmm. It's the idea of pulling out a GCF that's a constant. Mm-hmm. Okay, so what I'm going to do now is just to maybe make the parentheses a little bit easier on myself, let's go ahead and do math 9. Or actually, before you do math 9, let's go ahead and type that pi. Okay, so pi, I've got like a dark spot on my screen, but you can see the pi. And now I'm going to do math 9. So my lower bound is that decimal, that intersection, because you can see that my boundaries are from that intersection up to an x value of 1. Those are my boundaries, okay? So I've got that decimal, the 0.238 up to 1. So that was my a value up to 1. So I've got pi, and now I'm going to type r squared. My r squared is 1 minus e, and I think when I typed e, yeah, I did it as y1. So instead of me typing the e, I'm going to do 1 minus y1 in parentheses squared, okay, just to practice typing that, because that's a good way to do FRQs. So I'm going to do 1 minus y1 squared. So I'm putting it in parentheses. The y1, I'll show you with y2. So there's capital R squared minus 1 minus, and then you hit the alpha button, alpha trace. 1 minus y2 squared. So this is me doing capital R squared minus lowercase r squared. This is a great way to do FRQs so that you do not have to worry about typos, so you don't have to worry about complicated typing. You can type the complicated part in the y equals screen, and then this part is nice and clean for you so that your parentheses are easy. Okay, so capital R squared minus lowercase r squared, and then we're using our x's as variables. Everyone nice and comfortable with that? Yep. Enter 1.424, which is what we had. And Taya, if you want to try it with the pi's in there, you can do the same thing. So math 9, and we can do a to 1, and we can actually type it. So we can do pi 1 minus y1 squared minus pi 1 minus y2 squared, and you can see that you get the exact same answer. So it really, it's good to practice though, because in an FRQ it doesn't matter if you take it out or not, but in multiple choice answers they might pull the pi out. So it's good for us to recognize, oh, that's another way to write it. Yeah. Okay, how do you guys feel about that one? Does that make sense? How they did it? Okay. So this is where the capital R and the lowercase r came from. How'd you guys feel about part C? That was okay? A couple different ways of doing that problem, so it just is kind of how you finagle it to make it kind of work, for you. Okay, so that assignment, we feel comfortable with volumes of revolution. We feel comfortable figuring out the difference between the disk method and the washer donut method. We feel comfortable recognizing the top minus bottom, the right minus left. We feel comfortable with that. What questions do you, Reagan, do you want to do some other problems? Okay, we can do that. We can do that. Okay, let's do perpendicular cross sections. Which problem should we do? How did you guys do on this part? The notes? Good? Did everybody print it ahead of time, because those pictures were, whew, not. That's fair. That's fair. Oh, that's fine. That's fine. Okay. Yeah, because these are hand drawn, and they were a pain for me to hand draw. So I was like, there's no. Thank you. They were very, and I'm not a drawer. They were very hard. It was very hard for me to do these and like sketch them and get them, and yeah, so I was like, they need to print these or they will die. So, because you have to be able to picture these to be able to do them. So anyway, when I realized that I had not texted it out the night before, I was like, oh no, that was not the day for them to not have notes. I felt so bad. Anyway. All right, which problems shall we go over? Yeah. Okay. So, focus. Focus. Okay. So we have number 5. X equals 4 minus y squared. Y equals 2/3 x minus 1. X equals 0. Okay, and then the grid went Okay. So, are we getting better at sketching these by hand, or is it like just really killing your brain every time? Killing it. This is where, did you guys do conic sections in pre-cal? I'm trying to zoom in and it does not want to zoom in. Zoom, can you zoom for me? Zoom for mama. Zoom for mama. Zoom. Zoom. Please. Please. Maybe more? No? Oh. Oh, you guys, I have to tell you. So my little cat hurt his shoulder, so he's been staying inside the house. And he is friends with everybody in the neighborhood. So this morning I was leaving my house and getting in my car, and there are these two ladies that walk their dogs every morning, and the dogs were like walking past as I was coming out of my house, and they got very excited when my door opened because they thought it was my cat, and they were very disappointed when it was me. And the one dog just sat down, like, I'm waiting for the cat. And the owner was like, that's a human. That's not a cat, that's a human. And he just was like waiting, and she's like, you can't just sit. Sitting does not make the cat come out. And my cat had been like running around, and he was just staying inside because his shoulder was tired. So he was like, nah, I'm done. I'm tapped out. I was like, I'm sorry. DJ, your friend is here. Come see your friend. Come outside. See your friend. He doesn't like me. See your friend. I don't know. It's like I have a real child. All right. 4 minus y squared. What is the, if this had said negative x squared plus 4, if that's what it had said, because this is kind of like it's just in backwards order, right? What would that have meant if it was in terms of x? If this was in terms of x, what would the plus 4 mean? It would have been shifted up 4, and then what about the parabola? It would have been upside down, right? Okay, so in terms of right and left, what does this mean? To the right 4, 1, 2, 3, 4. It opens backwards, so it opens to the left. Okay. So parabolas, I don't know if you guys have picked up on this, but they grow by odd numbers. So it grows by 1, and then it grows by 1, 2, 3. And then it grows by 5 after that, but we don't have space, so I just did 1 and 3. It goes 1 and then 7, and then the next one after that is 27, so we usually don't draw it. It's if you counted, so it's 1 and then 7, but if you went back to count from the beginning, it'd be 1 and then 8. So it kind of depends on where you're counting from. Square root is the same as parabola because it's just a sideways version. So 1, 3, 5. Yeah, 1, 3, 5, 7, 9. Yeah. All right. So there's our sideways parabola. I think I wrote this backward. Oh no, it was like this. Okay. So this starts in -1 up 2 over 3, up 2 over 3. Down 2 over 3. How nice of them to give us one part of it in terms of x and one part of it in terms of y. You jerks. Okay, so we've got, let's go ahead and do it in terms of y first. Let's just make sure everybody's good. This is a good one just to like get our brains back in it. So they said, set up the integral and find the area of the region bounded by these two shapes with respect to y and then with respect to x. So let's do with respect to y. So we have the first equation is already written with respect to y, x equals 4 minus y squared. And then how do we write the other one in terms of y? Because it's written in terms of x right now. So we have y, I'll add the 1 over, so I've got y plus 1 equals 2/3 x. And then what do I do? So x equals 3/2 y plus 3/2. Okay, so there's our two equations. What are, now we don't have the bounds. Not quite. We don't quite know where they intersect. Well, but so this has to, for this one, the bounds have to be not oh, that's right, x equals 0. Sorry, I forgot about that. I forgot that that was another curve that was given, x equals 0. It's got to stop there. Okay. Oh, I wrote it right here, I just didn't use it. Okay, x equals 0. Okay. Oh, it was graphed for you. Silly Miss Rice. Well, it was good practice. Okay, so there's the problem. So if we write it in terms of y, what are the bounds that we're using? Okay, -2. So here we've got y equals -2, and then 1, y equals 1. -2 to 1, okay. And then what do we have? Okay, so right minus, yeah.
So far what you're doing isn't what was on. Because there's like a thing where it changes from -2 to -1 because they're like the
Yeah, so we have to break it up. That's what I was just looking at. We have to break it up because the right minus left switches. And it switches, hold on. Is orange a good color? It switches right here. It switches right there because, so you have parabola minus line, right? You guys see that? Parabola minus slanted line. But then over here you have parabola minus x or y-axis. Does everyone see that? Parabola minus y-axis. So we have to switch this. Okay, so it's not -2 to 1. It's -2 to what? Yeah. Okay, -2 to -1. -2 to -1. Are we comfortable with that? So, yeah. So, hold on. Let me zoom in manually because my Zoom isn't working. Okay. So if we do right minus left, it's because we don't have two curves, we have three, right? We had a parabola, we had a slanted line, we had a parabola, we had a slanted line, and we had the y-axis. Does that make sense? So if we had just been using the parabola and the slanted line, then we could have done the whole thing, but we would have had to figure out this intersection over here. And we would have done this intersection up to 1, and we would have done parabola minus slanted line, and that would have given us the whole problem. But we didn't have that. We had 3 curves to use, okay? So if we had 3 curves to use, then we do, okay, the parabola is on the right, the slanted line is on the left, until you get to this bottom part. Because this bottom part isn't bounded by the slanted line. Do you guys see that? The slanted line is not used on the bottom part at all. It's the y-axis. So for the bottom part, we can't say parabola minus slanted line because the slanted line isn't used. That would be too much area. Because I was looking at it and I was like, if I do parabola minus slanted line, that's wrong. I saw the y-axis there, and so my mind was like, oh, that's not quite right. So right here is where I see, oh, it's the parabola minus the y-axis. You see that? So that's how I knew that's where I should draw my orange line, is because that's where it switches, and that's the point right there. That's the y value where the y-axis and the slanted line come together. That's where the switch happens. Does that make sense? So we have this part right here is parabola minus y-axis for right minus left. And this part right here is going to be parabola minus slanted line. Does that make sense? Okay. So -2 to 1 is going to be parabola minus y-axis. Make sense? Okay. Plus -1 to 1. So this is below the orange line is what we just did. Now we're going above the orange line. And then we've got parabola minus slanted line. Okay. How's that? Make sense? Okay. So right minus left, right minus left. Comfortable? Okay. Now, let's go back and let's look at with respect to x. X does the same thing, but it does it in a different spot. Okay? So, with respect to x, we can use the slanted line the way that it's already written. This one actually gives us a bound, so it's not going to ruin, it's not going to be used as one of our curves, it's just going to be used as a bound. But up here we have to rewrite this. So we've got x equals 4 minus y squared. Let's go ahead and solve for y. So what should I do when I solve for y? Okay, x minus 4. Okay, negative x plus 4. Square root. Now when I square root, what do I put in front of the square root? Okay, so we've got two curves from this one equation. We have y equals the positive square root negative x plus 4, and y equals the negative square root negative x plus 4. So we got one curve, two curves, and then y equals 2/3 x minus 1. So just like when we did it with respect to y, we had three curves. We had the parabola, we had the slanted line, we had the y-axis, that was three curves. We again have three curves, but they're three different curves. So we have the top half of the slanted parabola, we have the bottom half, sideways parabola. We have the top half of the sideways parabola, we have the bottom half of the sideways parabola, and we have the slanted line. Does that make sense? Okay, so I'm going to grab a different marker. Can somebody tell me what x value, what vertical line splits the problem in half? Or not in half, but what vertical line splits it? It's at 3. Right here, this is where it gets split. Not in half. That's why I said in half and then I corrected myself. So it splits it there because we have top minus bottom. So here you have a slanted line on top, and then you have the bottom of the parabola, the bottom half of the parabola. So top minus bottom. And then over here, the slanted line is no longer being used in the bounds. It's the top of the parabola, top half. So here it's slanted line minus bottom half of the parabola, and then over here it's top half of the parabola minus bottom half of the parabola. We make sure we're not using this because we're not using the top half of the parabola to this over here, this over here, this, this. Well, because we use the bound of x equals 0. Uh-huh. Mm-hmm. Yeah, before the thing that kept us from getting over there was that we had the minus 0. We were doing right minus left and we were minusing 0 and that kept us from getting over there. Now the fact that we're doing top minus bottom, the fact that we're doing it in terms of x and we have a boundary of 0 is what's keeping us from going over there. Mm-hmm. So now in terms of x, we're going to say, okay, our lower boundary is 0. And then if we're doing to the left of the green, what's our upper boundary going to be? 3, because we're doing to the left of the green. Okay, and so we're doing top minus bottom. So what's the top going to be? Okay, and then what's the bottom going to be? Uh-huh. Yep, very good. So top minus bottom. Okay, and then how do we do to the right of the green? Uh-huh. Yep, very good. How your brains feel? I think it will happen. I think they'll give you one where you have to split up the area. Yeah.
Tell me what I wrote down is right. So I said for respect to x, we would find y equals, and then and you would use functions with x as a variable inside it, like when you're doing an integral, and you do top minus bottom, and then you use x values for the integral.
Yep.
And then I reversed it for the y.
Yep, that's exactly right. Yep. Yeah, it is confusing. All right, what's another problem we need to go over? Yeah. Okay, so the next problem says we're doing an object that is bounded by x squared plus y squared equals 100. So x squared plus y squared equals 100 is just a circle. And it's a circle centered at 0 that has a radius of 10. So yeah, that's something that you would have known from just after that 6, 7, 8, 9, just those problems. You'd know that from Math 3. Math 3 is when we learned about that. You would probably know it. That's why I was asking about pre-cal if you guys went over conic sections. When I taught pre-cal, conic sections were still a big part of it, and you'd know that from there as well. So circles, the form of a circle is x minus h squared plus y minus k squared equals r squared. That's like the form of a circle where you can see like what the center of the circle is, what the radius is. And so this would tell you that the center of the circle was 0, 0, and that the radius was 10. So since there was nothing here, it'd be like, oh, x plus 0 squared, y plus 0 squared equals 10 squared. So center 0, 0. Is that ringing a bell? Yeah.
There's like online a list of like good basic formulas to know in general for like advanced math. Like things you might not even use much in calc, but then would at one point because it's like logical for you to remember.
Yeah, basic formulas. Let me look and see what I can find. Yeah. Yeah, they yeah, I'm sure there's resources out there, but okay, so there's a basic sketch of it. So if we were to take this equation and solve for y, just for the next set of problems, then we would have y squared equals negative x squared plus 100. Does that make sense if I subtracted the x squared over? And then if I square root both sides, I get y equals the square root of negative x squared plus 100. I get a plus minus in front of it. That would kill a, hold on, that would kill a something, kitten.
How does that not work?
Because the plus in the middle. There's a plus in the middle, so that's not how the math works. Yeah. Yeah, please don't square root the things inside. So the top equation of this is the positive square root of negative x squared plus 100. The bottom of this is the negative square root of negative x squared plus 100. So if you wanted to graph it on Desmos, you could just type in x squared plus y squared equals 100. If you wanted to graph this on your calculator, this is how you would have to do it. So if we were to type this in just so we can see it, we would do square root negative x squared plus 100. Although I do think the color calculators might have the ability to graph conics. The conics are circles, parabolas, hyperbolas, and ellipses. Conics are pieces of graphs that come from parts of a cone. Okay, so here's our circle. It doesn't look like a circle because our screen is rectangular, not square. But there's our circle. So the top half, the bottom half. So S, I always think of S as being like the slice, because it is, if you were to put all of the perpendicular, so a cross section is like a slice of bread. So when you take one slice of bread and another slice of bread and you put all the slices of bread together, that's how you get something that's 3 dimensions, right? You get like a rectangular prism, like a loaf of bread kind of looks like a rectangular prism. Or if it's really round, like if you made it in a really round bread machine, then it kind of looks like a sphere, or maybe it looks like a cylinder or something like that, depending on... Yeah, Reagan's nodding. You guys are all laughing at me. Reagan's like, yeah, I'm with you. Absolutely, yeah, I'm with you. I support you, Miss Rice. I guess I know it kind of depends. Well, some bread machines like make bread that looks more rectangular, and some bread machines make bread that like looks round. Yeah, a bagel would look very round. Reagan is with me, man. I appreciate you, Reagan. Thank you. So I think of the cross section as being like, just like you took something and you like sliced, just like you made like a nice little slice through there. And so we're keeping with this in terms of x is top minus bottom, in terms of y is right minus left. We're still keeping with that theme. And so when we figure out what the s is, for this set of problems, we're going to do top minus bottom. Does that make sense, how I figured out the s, top minus bottom? So what I'm doing with this shape is I've got this top curve, which is the positive version, and I've got the bottom curve, which is the negative version. And so I'm just doing top minus bottom to make the slice. Okay, so top minus bottom, and then minus minus makes a plus. And what happens when I add these two together? It's just two of them. It's just the same thing. I got one square root and another square root, which is two of the same square root. So I've got 2 square root of negative x squared plus 100. So that's what s is going to equal. Okay. So then if you look at the front of your sheet at the top, that's where I gave you like all the little formulas that you'll want to have all these formulas on your cheat sheet, because these are like the most common ones that we're going to use for the different cross sections. So this is what we'll use now to figure out the different ones for squares or equilateral triangles or whatever. So now if we're doing a square, we're going to say that our bounds, negative 10 to 10, yeah. So left, negative 10 to right is 10. And for the square, if we look back at the front, the square is slice squared. Slice times slice. So what they're saying here is that the square, one side of the square is going to be from here to here. That's what the length is going to be. And then to make it a square shape, it's going to have to go up the same amount. Does that make sense? So they're going to figure out how long this side of it is based on how far this measures. And then to make it 3D, they're going to have to come up that same amount. Can you picture it? And so that's why it's s squared. Because this is going to be like your width across, and then your height or your depth or whatever is going to just have to match it. Does that make sense? Because it's a square. So that's why it's s squared. It's got to match it. So we're going to say, okay, let's calculate this. We're going to do 2 square root negative x squared plus 100 squared dx. And you would just type that in your calculator. Or you would do, if we were doing this as a calculator inactive, we would integrate it by hand. If we knew how to do this problem, this would be a u substitution because we have an inside and an outside. Does that make sense? Okay. We knew the integral because our graph had bounds, left to right, negative 10 to 10, and we're doing this in terms of x. So the way this problem is written, everything is in terms of x. This is definitely an x problem. Because of the picture. It's a circle. Depends on the...
Oh, because of like your graph.
Yep. Because of the way the graph is. Okay. The next one says equilateral triangles. So I just look at the front and I look at the formula for equilateral triangles and equilateral... Yeah, what's your question? Yeah, so isosceles right triangles. It says the side is the base. So what you have to picture is you just have to remember that an isosceles triangle is a triangle where the two sides are the same length. So I went ahead and I drew a picture, and they said the side is the base. And so I went ahead and drew it like, oh, these two sides are going to be the same. And that's what this is how I kind of led myself through it. I said, okay, the area of a triangle is 1/2 base times height. And then I knew like, okay, the base is one of the sides. That means the other side is the height, and those are going to have to be the same measurement. Yeah. And so that's where I was able to kind of derive the formula from there. Is like, oh, it's just 1/2 times the side squared. Does that make sense? Okay. Yeah, I think the only ones that are really counterintuitive are the semicircle versus the quarter circle, and the fact that a semicircle is a half circle and a quarter circle is 1/4 of a circle, but somehow the 1/4 of a circle is bigger than 1/2 of a circle. And that comes back to the fact that for the quarter circle, it's the radius is the entire slice, and that when you do half of a circle, it's the diameter that's the entire slice, and that's why it makes it smaller. So those are the two that like really mess with my brain that I have to like memorize the formula for, because I think they're like counterintuitive. They don't like, I wouldn't just remember that. So for me, this set of notes, when I first was like teaching this unit, this set of notes ended up being really helpful for me to like remember the formulas. Yeah. Yeah. Okay. Do we want to talk about any more problems on this assignment? Yeah. Yes. So, okay, so we look, here's the isosceles right triangle, right? So I said, I drew the picture and I showed you like the side is the base, side. Now, see how the hypotenuse is like not even considered? Okay, so if we look at 9, now when you do it, if you do an isosceles right triangle where the hypotenuse is the base, it totally makes the problem way different. So what I did here is I drew the triangle, and you can see I'm utilizing information you guys learned in Math 2 here. So an isosceles right triangle where the hypotenuse is the base means that it's a 45, 45, 90 triangle, which is a special right triangle. So I did this by hand. You could use SOHCAHTOA, because right triangles, you can always use SOHCAHTOA. You could use the Pythagorean Theorem, because you do know that those two sides are the same. So remember, this is the point in math where we say anything we've learned before is fair game. If you know that it's true, you can use it. So when you reach back and you say, I know right triangles, what do I know about right triangles? I got the Pythagorean Theorem, I can use the Pythagorean Theorem. So I used what I knew about a 45, 45, 90 triangle. And what I know about a 45, 45, 90 is that the two sides are the same and that the hypotenuse has a ratio. It's a ratio of 1 to 1 to 1 root 2. That's what I knew about 45, 45, 90. Hold on. If it's the same, you would get it if you did the Pythagorean Theorem, yes. And here's the thing is like, you could get like an unsimplified version and it wouldn't even matter because in the end we're going to get a decimal anyway. So it wouldn't even hurt you. Yeah, absolutely. So this is what I ended up doing, and the whole goal of this is to kind of create like what I did is I said, I know the length of this whole thing across the bottom because I'm using what I know about right triangles, so I could split it in half so I could find the height of the triangle. That was the whole goal. There's also, in pre-calc, you do learn how to get the area of a triangle without knowing the height, which is trig, and it's like sine of an angle. The information you have is side angle side, and it's sine of the angle. I'd have to look it up. I haven't used it for a while. I'm kind of rusty on that. Does that sound familiar though? It's like sine of an angle times the other two sides or something. It's like, so if you knew this was 45, then it would be this side times this side times sine of this angle. And if you knew, like, if you could figure out, like, oh, that has to be a 45-degree angle, you could use that also. So if we knew, and the slice, this is S is this, so you would have this time, but you'd have to know the root too. You'd have to know that was a root too. So there are multiple ways to approach the problem. It's just, for me, special right triangles are just in my head because I've worked with them a lot. So that was the first thing I did to say, oh, right triangle, SOHCAHTOA, I could figure that out because they know it's a right triangle with two sides that are the same, therefore it has to be a 45. So it just kind of depends on where you go with it, or maybe the first thing you went to was the Pythagorean Theorem because you said two sides have to be the same. If they're both the same, I can call them both x and find the third side. You know, so it kind of depends on like where you go with it. Yeah. But I will say, I mostly on AP questions, I've seen squares, I've seen semicircles. I've not seen a lot, like this is kind of a worst case scenario. I haven't seen a lot of this, to be honest. I've mostly seen shapes that are a little bit kinder. So this is a great problem to see on an assignment because it does make you think, and it's kind of a worst case scenario, which we want to see in practice first and not on a test first. Yeah. So, okay. Any other questions on that assignment? Absolutely. Yeah. Yeah. Totally. Okay. So I think for today, the plan for today was to do a washer method assignment, which I think I might waive and have us not do that. I think today I do want us to practice some FRQs though. Does that sound fair for today? Practice some FRQs. And then tonight's homework is the last concept we have, which is average value. And then we've got a review and then test on not Wednesday, but Thursday, because we are second period. So Thursday, not an exam, but test for this unit this Thursday. That is the plan.
What period are we next semester?